Hi, I'm Austin Percle. Today I'm the group lead for Group 3, and I'm going to be talking about the engine performance experiment. Here's a quick outline to give you an overview of the topics I'm going to cover and the order I'm going to talk about them. First, the introduction. Everybody pretty much knows internal combustion engines burn fuel to produce mechanical power. The type of engine we're going to be experimenting with next week is probably the most common, is the 4-stroke gas engine. If we can try to characterize the performance of the engine, we can learn something about the dynamic behavior, and hopefully that'll help us understand how to apply these engines better. So our objectives are to perform 2 tests. One is a variable speed with a constant load, and another is a variable load at a constant speed. So right into the theory. There are 4 strokes in the cycle: intake, compression, expansion, and exhaust. You can see in the ideal, it's assumed that expansion and compression happen isentropically, and that's pretty much not the case. Also, you can see that it's treated in the ideal case as if it's just air with heat going in and out, as opposed to actual combustion reaction happening in the cylinder. So that's going to cause some error here. Also, looking at the real case, the real cycle, you have to have an exhaust and intake to expel heat from the system. To test the engine, we're going to use a water brake dynamometer. A water brake dynamometer is basically a viscous coupling. The rotor is attached to an engine, and it turns in the fluid, water, and the fluid transmits power to the housing of the rotor. The rotor is set with a torque meter, which measures the torque, and we have a tachometer on the rotor. So we have the speed and we have the torque of the engine. From there we can get the power, and that's basically the 3 things we're interested in finding out. And lastly, you can adjust the load by adding more water will give you a higher load, more resistance, and taking water out of the system will result in a lower load. Which brings us to loading conditions. Basically, the load on the engine is going to impact its performance just as much as throttle or any kind of input variable. You can think of it as a loaded engine being really bogged down, or a free engine just running with no load. For example, if you increase the load at constant speed, it will require more torque to push through the resistance. And finally, the HP and torque versus RPM curve that we're going to look at in the results. You're going to notice that for every time the load is increased, the whole curve will move down by some increment. So relating power to torque, it's obvious from this equation that they're directly proportional, and they're related by speed here. And also from this equation, we can see exactly why horsepower overtakes torque as speed rises. Because for this, once N reaches 5,252, or gets higher than that, the horsepower is equal to the torque times a number greater than 1. So once it's past that speed, it will always be greater than the torque. Here we can see a curve of an engine that's pretty similar to the one we're going to be testing. This engine only goes to 3,600 horsepower. I'm sorry, RPM. That's pretty much what we're going to be dealing with. So we're in the lower region of the speed, and we're going to get like a nice general peak for the torque, and the horsepower is just kind of going to approach 12 or 13. This is really, it should be pretty close to what we get. And the equipment for this experiment, this is just most of the bare bones, the least you would need to simulate or reproduce this experiment. All you need is an engine, a dynamometer, a tachometer, a lever arm, and a load cell for the housing of the dynamometer, and a DAC. And when I say DAC, I really mean the whole computer and the software and everything, and the sensors But if you have all that, you can reproduce this experiment exactly. Now, safety, in all our labs, we always try to promote safety and be safe, but in this lab especially, since there's an engine, a combustion engine, it's pretty important. Of course, we're going to have ear and eye protection. There's an exhaust fan. The exhaust fan has to be on before really you do anything. That's the first step in the experiment. It's to prevent carbon monoxide. There are carbon monoxide sensors in the lab, and if they trigger, then we stop the lab and exit the room. Other things to watch out for are hot surfaces, not only on the engine itself, but hoses and pipes. They're going to be circulating hot water, so they're going to be hot. And of course, moving, rotating engine components, it's probably best to just keep your distance, stay away. Finally, the procedure. I went ahead and summed up the procedure into what I consider 4 main sections. When you're doing the experiment, it's going to be really important to go through each step individually. But for our general purpose here, I'm just going to give you a basic idea. First, you have to prepare the experiment. You have to hook up a wire from the motor, from the engine to the battery, and close the load valve. Then you're going to set up the PC. All you have to do is open the software and clear all the errors on the actuators and the sensors. So make sure that's all good to go. Then you can proceed to turn on the engine from the PC. Basically, as a safety precaution, we're going to turn it on remotely. Once it's on, you let it run for about 5 to 10 seconds on choke. Take it off of choke and let it run for about 5 minutes, just until it starts running smoothly. Once you do that, then you can start running the test and collecting data. If you're having problems starting the engine, try to backtrack through your procedure, and if you can't figure out where you went wrong, talk to one of the techs. I'm sure they'll be more than happy to help you. In conclusion, this experiment is really important because if we can learn about some of the dynamic behaviors and the performance of engines, we can apply them to different applications. We can know what engines are good for what purposes, or we can design an engine for some spectrum of operation, some specific design. So that's all pretty useful. Any questions?